This is P3 revision video for sustainable energy, energy transfer and cost calculations. So there's a couple of equations that you need to know for this section. One that relates current, power and voltage, and there it is. And remember, this is on the formula sheet, but you do need to remember the units, which are the standard ones written in yellow underneath. If you're unsure about rearranging it, there'll be a little link that will appear under that for a video about using the triangle method to rearrange the equations, so you can go have a look at that as well. And this equation is specifically for calculating power transfer in electrical appliances. And as we've already said, the equation but not the units are on the formula sheet, so you need to learn that power is in watts, voltage is in volts and current is in amps, but you don't need to learn the equation. Okay. It's worth noting that that equation isn't the definition of power, it's only power in electrical circuits. The definition of power is the amount of energy transfer per second, or the rate of energy transfer. And that's a much more general definition. But the top equation is useful when you're talking about electrical appliances. Yeah, so that definition in the green box applies to all situations. So if you carry on and do additional science, when you get into P4, you'll use that definition of power again. And another useful fact to remember, which they won't always tell you, is usually you'll be given numbers to put into these equations, but sometimes they're kind of in code. One of the codes is that if they say that something's attached to the mains, so plugged into a plug socket, then the mains voltage is 230 volts. So that's the number that you use for voltage if it's plugged into the mains. Okay, so let's have a look at an example using this equation. So a light bulb draws a current of 2 amps when connected to a 40 volt supply. What is its power? Now, whenever you get a calculation question, the first thing you should probably do is to underline the quantities you've been given, so you know. So there's current of 2 amps, 40 volts, and also we need to know what we're looking for, which is power. Now, you know in this case that we're using this equation because I'm using it as an example, but you've got to think about when you're in the actual exam paper, you're going to have a whole bunch of questions and there's a whole bunch of equations in the front of the booklet. You need to be able to identify which equation you're using. So the way we do that is to look at what we've been asked to find, power. Our equation is going to have power in it, right? And then we look at what else we've been given. We've been given current, and we know that this 40 here is voltage because the units, because you've learned units, right? Voltage is in volts. That means that we know that the 40 is voltage. So I'm after power, and I've been given voltage and current. So I search through the equation sheet in the front of the paper for an equation that's got those three in, and that's the one I use. Now sometimes you'll have to rearrange it, and sometimes you won't. But in this case, it's fine because power is on its own on one side of the equation. No rearranging necessary. All I've got to do is substitute in the numbers. So if we're doing it properly, we write the equation down again, copy it from the formula sheet, and then underneath you just put the numbers where the words were. So voltage is 40 volts, current is 2 amps. We multiply together and we get 80. But there is one thing we've forgotten, and that we've got to remember the units. Because we're calculating power, we know that the unit is the watt, okay, if we're using this set of units. They always go together. So if you put voltage in volts, current in amps, you'll get power in watts. Don't forget units. Sometimes there'll be units already put, so for example there'll be a dotted line for the answer and a unit afterwards. Sometimes there's not, and there will be a mark for the unit if you have to put it in yourself, almost certainly. It's an easy way to lose marks if you forget to do it. Okay, so that's a fairly simple example. Let's look at a slightly more complicated one. So a vacuum cleaner connected to the main supply draws 5 amps. What is its power in kilowatts? Okay, so underline our quantities again. 5 amps, we're after power again. Now, remember we said before that if you see the word main supply anywhere, that is code for 230 volts in the UK. Okay, so that's how we know that one. So we've got our 230 volts, we've got our 5 amps, and we've got our power, so it's the same equation. And we know that 5 amps is current because the unit is amps. Okay, and amps is the unit of current. So we write our equation down again, we do our multiplication again, we get our answer again. But we're not done, because this time we're after power in kilowatts. The calculation we've done so far will give us power in watts. Because we've used voltage in volts and current in amps, we will get power in watts. This set of yellow units goes together. So what we need to do is to take our answer and convert it into kilowatts. Okay. And the way we do that, there'll be a separate video eventually about converting units, which I'll link on here when it's done. But basically, if you're making the unit bigger, then the number needs to get smaller. Now, a kilowatt is 1,000 watts, so we're making the unit 1,000 times bigger. That means the number, the 1,150 at the front of it, needs to get 1,000 times smaller to compensate. Because what we're really doing is we're writing the same thing down, the same amount of power, in a slightly different way. Okay, so this is what we do. 1,150 watts, take it, divide it by 1,000, and that will put it in kilowatts. So it's 1.15 kilowatts is the answer. Do be on the lookout for these units. They love to throw in little tricks with units in these questions, so be on the alert for it. Okay, so that's power, voltage and current. The second equation in this module is energy, power and time. So power occurs in both of these. Okay, it's common to both equations, so you do have to be careful if you're calculating power. You could be using either equation depending what information you've been given. Now the tricky part here is that the equation is energy equals power times timing, it's on the formula sheet, but there are two sets of units. So there's joules for energy, watts for power and seconds for time. Those are the sort of standard scientific units that you use in normal scientific calculations. But because the joule is such a tiny unit of energy, there's also a set of units that electricity companies use, so that you don't end up getting charged for billions and billions of joules on your electricity bill. You get a manageable number if you use these units instead. Because the kilowatt is 1,000 times bigger than the watt, and because the hour, as we'll see in a second, is 3,600 times bigger than the second, that makes the kilowatt hour considerably bigger, right? In fact, 3.6 million times bigger than a joule. So a kilowatt hour is actually 3,600,000 joules. Okay, so that means it's a much larger unit. You don't need as many of them to sort of write down the same amount of energy. So be careful with this. You can't mix and match. You either need to use the top row of units, right, the joules, watts and seconds, or the bottom row, kilowatt hours, kilowatts and hours. Not both mixed together. Okay. You also need to be aware that a kilowatt hour is often called a unit of electricity. So if anywhere in a question it refers to a unit of electricity, it means 1 kilowatt hour. It's another little code. Another useful thing to remember, as I've already said, is time conversions. 60 seconds in a minute, 60 minutes in an hour. So that means overall 3,600 seconds in an hour. Very useful one to remember, or just work out on the spot. So that's your sort of summary for energy, power and time. So we'll look at another example calculation now. Oh, and worth remembering as well that, again, the equation but not the units are in the formula sheet. So here's our example. An electric kettle with a power rating of 2,000 watts is left on for 180 seconds. How many units of energy are transferred? So, again, underline our key quantities. Power rating 2,000, 180 seconds. Units of energy is what we're after. Okay? We know that 180 is time because it's in seconds. I know that one's fairly obvious, right? So, as we're after units of energy, we've got to select which set of yellow units here we use. Because we've been asked for units, which is kilowatt hours, okay, we need to use the bottom set. Okay, so if we're getting energy in kilowatt hours, we're going to have power in kilowatts and time in hours. And we don't have either of those at the moment. We've got our power in watts and we've got our time in seconds. So the very first thing we do here is convert the quantities we've been given into these units, kilowatts for power and hours for time. So just as before, we're going watts to kilowatts, so the unit gets 1,000 times bigger, so the number gets 1,000 times smaller. 2,000 watts, 2 kilowatts. Again, we're going seconds to hours, so the unit's getting 3,600 times bigger, so the number gets 3,600 times smaller. So 300 seconds is 0.05 hours. So now we've got our quantities in the correct units. We can pull out the equation, stick them in the right place. Okay, 2 kilowatts, 0.05 hours, 0.1 kilowatt hours, or 0.1 units. There is our answer. So this is why it's so important to be on the ball with your units. Sometimes you have to do these conversions. Okay? Very rarely will you get a question without a conversion in it, it seems these days. So it's really important that you know how to do it. As I said, look out for the separate video on that coming later. Okay, a little point about electricity meters. One way that you can get the energy consumption of a device is that calculation that we just talked about. Another way is reading off a meter. So the dial on a digital electricity meter looks a bit like this. The little red digit on the end here is the 0.1 kilowatt hours. So it's just like a normal number. So this reading is 34,725.4 kilowatt hours. Usually when you get questions like this, they'll give you two readings, because if you're paying an electricity bill, what happens is you read the meter at a certain point, and then you read it later on, and you are charged for the difference. So here's a second reading from the same meter, and what we're going to do is show how to calculate your electricity bill. So obviously, in order to work out how much you're paying, you also need to know how much each unit of electricity costs, and you should be told that. You won't be expected to remember. So here we're saying 14p. Okay, what would the bill be between these two? So the first thing you've got to do is work out how much has been used. Well, it's gone up from 34,725.4 to 34,812.6. So we need to take the difference between those two to work out how much has been used in the house. So you often find under the sink is one place you'll find these electricity meters attached to the outside of a house. Quite often another way to go. Under the sink's water meters, I know what I'm talking about. So 87.2 kilowatt hours is what we get here by doing that subtraction. And then all we do is we multiply it up. Now this equation, this cost units used and price per unit equation, is not on the formula sheet. You're kind of expected to either remember or work it out, or they think it's so obvious that you don't need to. So you just take the amount that you've used, multiply it by the cost per unit, and you'll get the total cost. And you might be asked for it in pence or pounds. Probably best to round to the nearest 1p. But yeah, don't forget this cost unit price per unit equation is not on the formula sheet. You will need to remember it. Okay, so now time for you to have a go. What we're going to do now is just give you a calculation that covers all the things we've done. Okay, so pause the video, have a go at this, and then we'll go through the calculation afterwards. Just be careful with the units again. Okay, so what we're looking at here then is electric toaster draws 6 amps from the mains. What is its power rating in watts? Well, again, we've got to remember that mains is 230 volts. So for voltage we use 230. For the current we're given 6 amps in the question, 1,380 watts. Okay, and we know we're using the power voltage current equation because that's what we've been given. We've been given a current. We know it's current because it's in amps. So we can't use the top equation for this. We couldn't rearrange the top equation and do power equals energy divided by time because we don't have the energy and we don't have time either. All right, so we have to use the bottom one. Okay, number 2. Toaster takes 3 minutes to toast a slice of bread. How many units of electricity does it use? Well, again, we're after units, so we've got to be in our standard second set of units, and I've not put them up here because this is what you'll get when you're in the exam. You won't get the units, you have to remember. So if we need energy, we're using the top equation now because we've given time 3 minutes, and we've calculated in the first part the power rating, so we've got that as well. So we need to put our power rating into kilowatts and our time into hours. So again, we do the conversion. The power is 1.38 kilowatts. We take our 3 minutes this time, so we're only divided by 60 because we're doing minutes to hours. And again, gives you 0.05 hours here. And then we put them through the equation, so we end up with 0.069 units. And the final part is just multiplying that 0.069 up by 12p in this case, because each of those units costs 12p. So that gives us 0.8p, rounding to the nearest 0.1 penny, for our slice of toast. Okay, hopefully that's been helpful for summarising how to do the equations in P3 for you. Once again, if there's one thing to take away from it, it's to be really, really careful with the units, because this is a place where they do matter a lot. Thanks for watching.